So now we are talking about conditional probability. So a reproducing kernel Hilbert space and omega with a kernel is a Hilbert space of functions with inner product. Its element satisfies the reproducing property. This is the reproducing property, and this is our kernel. So we mapped our distribution from P to mu of P in the Hilbert space, and this was our distribution space. We mapped it to Hilbert space, and so imagine this mean as a vector of size 64,000, because we have an image of 64,000 pixels. So this is a feature map, let's say. So you see, it is implicit because it is not rational to make an explicit thing for several images. For example, in Google DeepMind project, you cannot do that. So we use this where the distribution is mapped to its expected feature map. So we use the Ray's representation theorem, and this is the expectation of f of x. We talked about it in previous lecture. So when we want to map a point, we use mu. But if we want to map a conditional distribution or a joint distribution, then we should go to a tensor product space. And we don't need this because we can, for example, with the analogy to the graphical models, we just need the relation mutual information, two of them. We just need the relationship between two of the nodes in a graph. So we don't need, in practice, this is not tractable. So we use either a product space for joint distribution, or for simple distribution we use mu. And you will see in the next lectures that you can find such equivalence of everything that you have done for sum rule, product rule, base rule. You do it with other variables that is meaningful in Hilbert space, such as covariance, cross covariance, and those stuff. So when we talk about the tensor product, we mean their dimensions is like this. For example, 5 by 3. So this is you can think about it as an operator in the Hilbert space. We don't need the tensor product for matrices because that's just enough. All Hilbert-Schmidt theorem, everything. You just need to understand the tensor product of two vectors. So we define cross covariance by expectation of this is feature map, the tensor product of them. So that why this is important, because you can solve this. You can have such a great representation. Or you can consider the covariance. You said covariance operator is this CXY. Or you could define the covariance operator as just an animal in the vector, in the product space, in the tensor product space. So as usual, we approximate everything. So this is the empirical estimation of both mean and covariance operator. So you see these points, they go to mu of x in reality. But when we approximate it, there is a difference between these two. if we reduce this mean, then our approximation, our empirical experiences is very good. So if you're familiar with maximum mean discrepancy, which we have found that it is much better than KL divergence, Jensen divergence in GAN architecture, general adversarial networks. KL divergence, we use it for autoencoders, and finally we found that maximum mean discrepancy has lots of benefits in comparison, because the problem with KL, because it becomes physicists don't like it because it gets infinity. You see, how do you compare this? How do you say this? You know, when you say, what if this one is 0? You know, what if their supports are different? It gets infinity. Jensen is talk about of square root of 2, but maximum mean discrepancy is more general. You will see in 2030, everybody will talk about it. Okay, so when you write this difference, you can, instead of working with explicit feature maps, use a trick. If you just solve and work on it, you can write it as a kernel functions. So you don't need to know the implicit feature maps. You don't need to know that. Use the kernel idea. Once you define that, for example, Gaussian kernel, Laplace kernel, then everything is enough. And the condition in 2009, this one from Japan, and they found that you can represent it like this. And this is the covariance operator, and you can do conditional stuff such as conditional distributions as well. So I said that mu of y is equal to phi dpy. But if we condition on that, there is nothing happens, just the conditional things. Again, we have their implicit map, and we can just use this, and you can substitute this here, and you can have a conditional mean embedding as well. For canonical delta kernel, just for intuitions and nothing more, we can simply see such a beautiful things. And so instead of mapping Q and Q to the Hilbert space, which I told you mu P mu Q, here we're mapping conditional distributions to their conditional means. So we have just generalized the idea. And we can also write empirical approximation like anything we did. And we have kernel embedding of conditional distribution as well. So you see that in the original mu embeddings, original empirical estimations, we use something like this, 1 to the n. But here, this is just a weighted sum of those stuff. So when we talk about conditional mean embedding, it's just the old things, the old empirical approximation. But here we just used, it is just some weighted approximation. And this weight we have calculated to show it is this one. And an alternative solution using regression. I mean, this guy has shown in 2012 that you can represent that as just a simple regression. This could be useful if you want to do some more technical, some more theoretical work on that. Is very, very useful. Then because you get the intuition, you get a very good intuition behind what we are doing in Hilbert space. Because here we are in Hilbert space of functions, for example. Here, space of distributions. But here, when we look at this, we have a sense of what we are doing then.